When you think of the solar system, your mind probably jumps straight to the heavy hitters, the massive, fiery sun, giant gas planets like Jupiter with its iconic storm, or Saturn cradled inside its glowing rings. But scattered throughout the vast cosmic empty space are millions of silent, floating worlds that hold the ultimate secrets to how we got here. These are asteroids. At their simplest, asteroids are rocky, airless remnants left over from the formation of our solar system roughly 4.6 billion years ago. Think of them as the leftover construction debris from when Jupiter, Earth, Mars, and the other planets were built. When a giant cloud of gas and dust collapsed to form the Sun and planets, most of the material was swallowed up. But small fragments of rock, metal, and ice were left tumbling through space, stuck in a dynamic cosmic dance. Unlike planets, asteroids aren't large enough to have squeezed themselves into clean, smooth spheres under their own gravity. Instead, they look like giant, lumpy potatoes floating in the void, pitted with deep impact craters, jagged ridges, and scarred from billions of years of collisions. They range in size from tiny boulders just a few feet across to giant mini-worlds like Ceres, which spans nearly 600 miles wide and is so large it's actually classified as a dwarf planet. Most of these space rocks live in a massive highway between Mars and Jupiter known as the main asteroid belt. This region contains hundreds of thousands of known asteroids, and likely millions of smaller ones. You might picture the asteroid belt like a sci-fi movie, a dense obstacle course where spaceships are constantly dodging flying boulders. But in reality, space is unbelievably vast. If you were standing on an asteroid in the belt, the nearest neighboring asteroid would usually be hundreds of thousands of miles away, looking like nothing more than a faint star in the dark.
So, what are asteroids made of? Scientists group them into three primary visual and chemical flavors. First are the C-type or carbonaceous asteroids. These are dark gray, rich in carbon compounds and water ice, and happen to be the oldest objects in the solar system. Next are the S-type or stony asteroids, made mostly of nickel-iron mixed with magnesium silicates. They dominate the inner belt and appear much brighter. Finally, there are M-type or metallic asteroids, which are almost pure nickel and iron. These metallic giants are believed to be the shattered cores of ancient protoplanets that were smashed apart during the chaotic early days of our solar system. Now here is where things get genuinely wild. Asteroids aren't just lonely, isolated rocks. They can actually have their own moons. For a long time, astronomers assumed asteroids were far too small and weak in gravity to capture or hold on to satellites. That belief changed forever in 1993, when NASA's Galileo spacecraft flew past a 20-mile-wide asteroid named 243 Ida. To everyone's astonishment, images beamed back to Earth revealed a tiny, 1-mile-wide rock orbiting steadily around Ida. Scientists named this miniature natural satellite Dactyl, marking the first time a moon was ever discovered orbiting an asteroid. Since that historic flyby, we have discovered over 400 binary or triple asteroid systems. Some asteroids even have double moons. For instance, the giant asteroid Sylvia has two small moons named Romulus and Remus. How do these asteroid moons even exist? Usually, they are born from violent space collisions. When a smaller asteroid slams into a larger one, debris flies off into orbit and slowly coalesces into a companion. In other cases, fast-spinning asteroids fling off loose rubble from their own equator due to centrifugal force, forming a ring of debris that eventually gathers itself into a tiny moon. This brings up a fascinating reality: asteroids are far from static, dead lumps of rock. They are dynamic worlds. Some asteroids aren't even solid rock at all, but rather loose, rubble piles, collections of thousands of boulders, gravel, and dust held together very loosely by weak gravity. When space probes like NASA's OSIRIS-Rx visited the asteroid Bennu, scientists discovered that stepping onto its surface would feel less like landing on hard rock and more like sinking into a ball pit. Why do scientists spend billions of dollars sending spacecraft to study these distant remnants? Because asteroids are pristine cosmic time capsules. Because they haven't changed much since the dawn of the solar system, analyzing their mineral and chemical makeup gives us a direct window into the exact recipe that built the planets, including Earth. Even more exciting, many carbon-rich asteroids carry complex organic molecules and water locked inside their minerals. Many scientists believe that early in Earth's history, a heavy bombardment of asteroids delivered the vital water and organic ingredients that ultimately allowed life to sprout on our planet. Beyond science, asteroids hold immense potential for the future of human space exploration. Metallic asteroids like 16 Psyche contain iron, nickel, gold, and platinum valued in the quadrillions of dollars. In the coming decades, asteroid mining could provide the raw materials needed to build space stations, rocket fuel, and habitats directly in orbit without having to haul heavy supplies off Earth. And of course, we can't forget planetary defense. Asteroids occasionally cross Earth's path, and while catastrophic impacts are exceptionally rare, they have altered the course of life before, most famously 66 million years ago when a 6-mile-wide asteroid wiped out the dinosaurs. Today, missions like NASA's DART have proven that we can intentionally crash a spacecraft into an asteroid to alter its trajectory, giving humanity the power to protect our planet from future space impacts. From ancient planetary building blocks to miniature systems holding their own orbiting moons, asteroids are far more than mere floating rocks. They are historic records of our past, potential hazards to our present, and stepping stones toward our multiplanetary future.